Okay, so I have got a PDF from some other reference book, which I'll be showing you here. So look, before that, I'll just write the normal Biot-Savarts law, which we had already learned yesterday on Sunday. So first, let me tell you about that. And we had applied that Biot-Savarts law for a loop also, current carrying loop. How to find out magnetic field at any axial point on the loop. So those things we had already discussed. I'll just write the Biot-Savarts law what we had learned last day. And what was the formula for that? And what was the formula for magnetic field at any axial point? Okay, so those things I'll write down here just for your recap. Okay, so if you remember, correct. Okay, yeah. So if you remember, Biot-Savarts law, we had learned that the magnetic field for any, so generally Biot-Savarts law for any arbitrary shaped wire you can take, okay, and that is actually infinite, that is of infinite length. Okay, so uniform wire, that means the radius of the wire may be the same. Okay, let us take like this. Like this. So if I take a small element of this wire, so suppose the current is flowing in this direction, so if you look in your book, you have to take the, see, multiplication. So this ideal, this is called actually current element, and this is as a whole a vector quantity, ideal, and the direction of that actually will be, if you draw a tangent at any point, suppose here I am taking an element, so here you have to draw a tangent, okay, to that point of the wire, and you have to take the arrow of that tangent in the direction in the direction of flow of current. Okay, so that's why I have taken this way. Otherwise, tangent can go like this also. I could have taken like this. I haven't taken because my current direction is this way. So this will be the true direction, upwards. Okay, so according to Biot-Savarts law, if I have to calculate magnetic field, so this is suppose an infinitely long wire. So this has a length, suppose dl. So this is as a whole, idl is called current element, and this is the source of the magnetic field induction or magnetic field. As you know, like in case of electrostatic Coulomb's law, the force field, the source of the electric field is actually the charge, but in this case the current element, or some will learn that a current element or a current loop can act as a source of magnetic field. So in this case, if suppose I have to calculate magnetic field at any point r, at r distance, okay, at any point p at a distance r, so here magnetic field will be into the phase, and that we had already derived that dB, we have to write, actually we can write mu0 I by 4 pi.
4 pi.
Mu0, yes, dl cross
dl sin theta
cross, yes, dl cross r by r cube. So it is in terms of vector. If you do write this as scalar quantity, then ideal sine theta
by r square, 4 pi r square.
4 pi r square. So this was the scalar format. Okay, and using this, actually we had calculated uh, magnetic field for a current carrying loop. Okay, for a current carrying loop of radius, some radius, suppose r, at any point, any axial point. This is the center of the loop, axial point. That means at any point here, suppose this is r. Okay, so let us take this as x. So that will be all right. So x, suppose this is a point p, and here you are calculating the magnetic field. Do you people remember what was the expression for this? Who can tell? Kirtana, what is the expression? Actually, the expression is mu 0 I. If this is the radius of, this will be r square divided by 2 into x square plus r square whole to the power 3 by 2. So this was the expression for the magnetic field at any axial point. Okay, at any axial point. So these are the expressions which we'll be using, or the theory which we'll be using to solve the problem. But before that, what I thought, I'll just uh, tell you that, so that was the infinite wire and arbitrary shape of wire, okay, in the Biot-Savarts law. But this Biot-Savarts law, when we apply for a straight wire, Biot-Savarts law, so this is not there in a book, in the textbook, NCERT textbook, but this is very important for those who, like, actually numerical problem will come even for you people also, and those who are aspiring for competitive exams, various competitive exams. So Biot-Savarts law for a straight, for an infinitely long, infinite, even finite also fine here, infinitely, infinite straight wire. Okay, straight wire. Today we will discuss this first as a theory, then we will apply straight wire. Okay, so this is our first topic to discuss. So let me show you the PDF where I have the figures and everything. Okay, so let me just take this figure that will allow me to save some time. Otherwise, I have to draw all the way. So I'll take this figure. Okay, so as you can see, I have taken here a finite wire, or even this Biot-Savarts law is well applied for infinite wire. So suppose this is a finite wire for the time being. Then I'll tell you what will happen if the wire is infinite. So for the time being, you consider x and y a straight wire, and this is a finite wire. Okay, this is a finite wire. Okay, so what I have to do, I have to calculate magnetic field. Suppose at any point P, which is a distance away from the wire at this P. Okay. Now what I have to do, I'll just uh, I'll just take an element. Okay, take an element, current element. Okay, and then first let me write the expression for the magnetic field due to that element itself. at any point P, okay, at that point P. So first we'll write the Biot-Savarts law for that particular element, current element. So before that, let me tell you that Q. Let us uh, draw a perpendicular from this point P to P on this XY wire, this straight wire. So which touches here, touches the wire at Q point. So that means this is having 90-degree angle. And let us uh, assume that the angle between DL and the radius vector, what does that mean? Radius vector is the vector drawn from the current element to the point P, where I am going to calculate the magnetic field for this wire. So this is the radius vector and this is the element, and between them let us take the angle theta, and this angle, this angle, let us take as phi. This angle as phi. So now obviously we have taken this point as P. From P point to, so OP is the radius vector. OP is the radius vector. Okay, and this OQ, the length of OQ, that means from the foot of the perpendicular to this element. Okay, suppose this is length L. Okay, now the current which is flowing in this wire is suppose I. Now I have to write the Biot-Savarts law over here. Biot-Savarts law, as I wrote, I'll write the magnitude first. Okay, we know we can find out the direction, that is all right here for the straight line. So this is mu0 I, then dl sine theta by 4 pi, and here r means the distance from here to here, so this will be a square. Okay, so q to qp distance. Okay, this is a. Okay, so this is my expression over here. 0 by 4 pi. Okay, I'm sorry, this is not the a square now. This is actually the vector distance from the current element, so it will be r square. So mu0 I dl sine theta by 4 pi r square. So this is so suppose this is the length, so I have to take r square here. So this has a magnitude of the length as r. Okay, so this has r. I'll use this expression. Okay, now look this this angle phi. So if I take the triangle, O, Q and P, this triangle, look, theta plus phi will be actually 90 degrees. Theta plus phi will be 90 degrees. So what is the value of theta? Theta is 90 minus phi, 90 degree minus phi. So if I put it here, then I'll get sine 90 minus phi. That means my expression will be actually sine square phi over here. Okay, so sine square phi. Oh, sorry, cos square phi. Cos square phi. I'm sorry. This will be cos square phi. This will be cos square phi over here. Okay. Now, look, we'll write this one, what is r square. So cos phi, again from this same triangle, O, Q and P, if I write cos phi, what is cos phi? Cos phi is actually A by, uh, this is actually base, this is the hypotenuse, so A by R.
R.
A by R. Okay. So what will be R square? So R square will be A square by cos square phi. So if we put it here, if we put in place of R, okay, so what we'll get? Let me just remove this part, then I'll put the value of R square. So if I put the value of R square, look here, you get yes, so you get mu 0 I dl, then cos square phi. Oh, that's the problem. Okay, so this is not a cos square. I'm sorry. I'm just sorry. This was sin theta. So sin 90 minus phi will be actually sin cos phi. Okay. So now here I can write this as r square will be a square. So a square is here 4 pi a square, and
Cos Q.
cos square will go up. So you will get actually cos q phi over it. Cos q phi. Okay. Now I'll just see what is L, what is the relation between L and other things. So in terms of theta phi, I'll try to write. Okay, so look here, tan phi. Tan phi is actually L by A.
A.
Okay, perpendicular by base. So if I just take derivative of that, so dl will be A into sec square phi. Okay, I hope you people will be agree with me, and I can write d phi. I'm just taking a partial differentiation so that I get this. Okay, so I'll just remove this right hand part. Okay, so now I'll just put the value of dl also. Let me tell you. So this is mu 0 I, and then dl will be sec square phi, and here cos q phi. So cos q phi I'll write as cos q phi here. Okay, and divided by 4 pi a square. 4 pi a square, and here dl, another a will be here actually, a will be here in the top, so in the numerator, so it will go like, it will be like this. Okay, like this, because from dl you will get 1a. So if I just multiply a in the numerator, so 1 a will go out. So now look, sec square and cos square phi, so they will be reciprocal to each other. So this you get eventually, this will be cos phi. Okay, on d5 I have omitted, so d5 will be there. Okay, d5 divided by 4 pi a. So this will be your uh, magnetic field for this particular element. Okay, this particular element. If I take such many elements, okay, so then I'll get the magnetic field for the whole wire. So if I want to get for the whole wire, look here, this QP line I'll take as my reference line. Okay, and the angle of the count of the angle I'll take from that point. Okay, so if I go, suppose this is the wire, right? So this is the wire. Look, phi 1, there is something called phi 1. So phi 1 actually I will be counting like this, and the angle, top angle I'll count from this is QP line. So from here I'll count like this. Okay, so this angle, so if this is a reference or zero line for angle, okay, So this will be actually in this side it will be plus phi 1, suppose phi, this is phi, I think phi 2, this is phi 2 as it is shown here. So the angle count will be actually this way 1 and another one will be in this direction, okay, in this direction. So this is minus phi 1. So I'll just remove this first one, okay. So if I just do the integration, just look, I have to do the integration for just the angle itself. To get this, I have to do the integration. So phi is equal to minus phi 1 to plus phi 2, and this will be mu 0 I cos phi d phi, okay, divided by 4 pi a. Okay, so these are constant terms, so I can just take it, uh, take them out, and then if I do the integration, look, if you do the integration, you will definitely what you get is actually mu 0 by 4 pi a, and this will be sine of phi 1 plus sine of phi 2. Okay, okay, I'll just clean this portion. I'll clean this portion and write again here the final expression for the magnetic field. Okay, so let me write the final expression for the magnetic field. So B will be actually mu 0 I by 4 pi, and then sine phi 1 plus sine phi 2. Okay, so this will be, so 4 pi a here, 4 pi a. So this will be the final expression. And look what is phi 1 and phi 2 once again. You look what is phi 1 and phi 2. I'll tell you once again. See, yes, Edward.
Tell Jayant to mute himself. It's okay, sir. Now it's
okay. I think now it's okay. Yes, yes. So do you people understand this, or do you have any doubts or questions, comments, anything? So if you have any doubt, you can ask me now itself. So this is very important concept for those who are planning to write various competitive exam, because now I'll show you how we apply this formula for various problems. So this is for finite wire, okay? This is for finite wire. So now if I, okay, this is for finite wire. Look this is for finite wire. I'll take a few examples before I go for the examples. Let me tell you what happens when the wire becomes infinite. Okay. So suppose the wire is infinite. So what happens in that case? Who can tell? So when the wire becomes infinite, look, this becomes infinite. This is the point here, P, where I am calculating the magnetic field. Okay, this is the point. So this is the phi. See, I am calculating the angle phi 2 in this way, right? In this way, and phi 1 in this way. Okay. So if this goes and goes like that, so finally you will get like this. Okay. So if it is infinite, so your phi 2 will be 90 degree, and similarly if your wire goes like this, so to infinity, so your angle, this angle also, okay, this is phi 1, this also will be 90 degree. Okay, both will be 90 degree. So phi 1 and phi 2 if the wire is infinite. Look, then what we get is actually this mu 0 I by 4 pi a, and this will be 2, this will be 2, sine 90 sine 90, 1 plus 1 2. So what you get is this mu 0 I by 2 pi a. So this is the magnetic field. Okay, magnetic field near, almost near the middle point of the wire. Okay, near the middle point of the wire if you want to calculate the magnetic field for an infinite wire, for an infinite wire. Okay, This is the magnetic field at this point. Okay, but suppose the wire is infinite, but you take the point where you want to calculate the magnetic field at one of the edges. So what happens in that case? So suppose my P is here now. P point is here. So what is the phi 2 angle? Phi 2 actually will be 0. And what is your, so infinite one, that means phi 1 will be anyway 90 degree. That is all right. So phi 1 is 90 degree, but phi 2 will be actually 0. So for that case, you will get mu 0 by B is equal to mu 0 I by 4 pi A. For this case, if I take at any of the end point of the wire, okay, infinite wire, but I'm calculating the magnetic field at any of the end point. So it is actually the half of the magnetic field if you calculate near the middle point. Okay, midpoint, B midpoint. Okay, so this is the thing. So mainly you have to remember this expression. This is for finite wire, and with this itself you can actually extend this knowledge for infinite wire also. I'll I'll clean everything. I'll write the expression for this again, and I'll just make you remember once again that how do we take the angle. Angle we have taken from this reference line QP. So this, from here I have taken this way phi 1, which I had taken minus phi 1, and this way I had taken plus phi 1. Okay, so plus phi 2, plus phi 2. This is my reference line, kind of phi is equal to 0 over here. Okay, so from there angle calculation is actually or the direction of the angle I have taken opposite in the down, then the up. Okay, so these two things you have to remember. So when it is becoming infinite, so your this angle is actually increasing in this way. Okay, this way, and your phi minus phi 1 is actually increasing in this way. Okay, like this. So both are becoming 90 degree. Both are becoming 90 degree. So that is what you have to remember. Okay, otherwise all things are all right. Okay, so now I'll just take you through a simple example on this particular concept. uh, so you have to find out magnetic field at the center of a coil bent in the form of a square of side to a carrying current I. So this is the question. Do you people want to try this? So I'll just draw the figure for your sake. This is a square loop. Okay, suppose this is a square loop of side 2a, carrying current I, So you have to, suppose this is anti-clockwise direction. You can take whatever you like, the direction of the current. So at this point P, you have to find out the magnetic field. You have to find out the magnetic field over there. Okay. So how do you do that? Anyone can volunteer?
Sir, by applying formula for a finite wire.
Exactly. So what we got? Mu 0 I by 4 pi A sine phi 1 plus sine phi 2. So this is for the finite wire we have learned. Okay, so you have to actually know what is phi 1, what is phi 2, and what is this A. Look, this angle is actually, suppose this is the wire. If I take this is the wire, this is the wire, finite wire. Suppose this is A, this is B. So AB is the finite wire. Let us take first. Okay. So what we have to do, I have to draw the angle, and I have to know what is. So see, I'll draw like this. Okay. I need to know this distance. This is suppose Q and P. Okay, QP, and what is this angle and what is this angle. So these two angles you have to find out. And what is this QP length? So it is at the center, so it is 2A length. So lengthwise 2A, so it will be actually QP will be your A, simply A. And what is this angle? Since this is 90, this is 90,
9.
this is 90, all angles are 90 for a square. So this will be your, this is 90, this is actually perpendicular bisector, this line. Okay, AP line is a
40.
perpendicular bisector. So since this is 45, so this also will be 45 degrees. So similarly, this also will be 45 degrees. Okay, so your phi 1 and phi 2 both are actually 45 degrees. Will you be able to find out now? Okay, let us now apply. So this is for only one wire, for one wire. So if I calculate this, actually we will get mu 0 I by 4 pi A. 45 means is it 2 by root 2 like this, and actually it will be root 2
by
into mu 0 I, yes,
4
4
pi.
pi A. Okay, so this is for one, yes, this is for one wire. If I take, I have to calculate for all the wires, right? And look, actually in this case you have to see the direction. You look at this point, all of them will be actually uh, for all of them the magnetic field is actually going out or coming out of the page, plane of the paper, right? Coming out of the plane of the paper. So all the magnetic field will be additive. Okay, for all of them the magnetic field will be additive. A, B, C, D, for AB, for BC, for CD, and DA. For all of them the magnetic field lines, actually magnetic fields are additive at this point. So you have to actually finally you will get the magnetic field 4. Suppose this is okay, 4 into this one. Okay, if I write this is B prime, so 4 into B prime, so you will get 4 into B prime is equal to root 2 into mu 0 I by pi into A. So this will be your actually magnetic field. So this is root 2. Okay, root 2. So this is how you have to apply this formula for finite wire. Okay, so this problem itself, if I just like with this formula itself, you can, I'll just give you. So this I have solved for you. I will expect you to solve one problem. Suppose this is question 2. A closed circuit is in the form of in the form of in the form of a regular hexagon of side A. If the circuit carries current I, what is the magnetic field? Magnetic field. Magnetic field induction. That means B. Magnetic field induction means B. B at the center of the hexagon. Of the hexagon. I'll just give you some 4 minutes. Okay, I would expect you people to solve. Priyadarshini, all of you can try this problem for a hexagon. Actually, I'll just give you a hint. Look, the same formula you have to use here also. You have to write. You have to draw. First of all, you have to draw a regular hexagon. Okay, and same formula after that you have to apply. So mu0 I by 4 pi a sine phi 1 plus sine phi 2. Okay, this is the formula you have to use. Once you get for one wire, you have to suppose this is B prime, and for all the wires you have to multiply 6 into B prime. So you have to find out basically what is B prime.
Sir, for one wire, it is mu naught by 4 pi into 2i by root 3.
Mu naught.
Mu naught 2i by.
Okay, even. Okay,
for one
just
wire.
let me write mu naught 2i
by.
Okay.
4 pi. Under root 3.
4 pi.
Under root 3.
Under root 3.
A.
Okay. So you have to multiply 6 over here. Okay.
Yes,
so
sir.
Then you can write this as 2 into 3. So you will get here root 3. You multiply root 3 over here. Root 3 you get, and 4 goes out. Okay. So what you get is actually mu0 I by pi a. Okay. Into root 3. Yes. So the final answer, I think then you people also try. Okay, I'll not solve it. I have given you the hint. If people try, I'll just write the final answer for this. Kirtana has got correctly. Okay, so simply you have to find out what is phi 1 and phi 2 and what is this a. So these are the parameters you have to find out from the figure. If you draw a regular hexagon, from there you have to find out this a. Okay, then what is the final answer? So final answer is this: root 3 under root 3 mu naught I by pi into a. I don't know, you people are not saying me anything, yeah, or others are not saying anything. I don't know whether they have understood or not. Nikhil, what about Nikhil? Are you able to understand? Nikhil, then Priyadarshini, and all others. If people can give you feedback, if you don't understand, kindly tell me so that I can repeat that. Okay. Okay. If you are not saying anything, if you people are silent, then I'll assume that you people have understood the problem. or understood today's discussion. Okay, Nikhil, are you there? I think. What about Priyadarshini? Okay, I have got from Sevi Chakravarti. Okay, in this Sevi Chakravarti, she had told. Okay, uh, I don't know. Are you okay? Mhm. I've got your answer. Okay. What about Sania? ISL Sania. Do you understand this problem? What about Sadbi Neeli? Okay, I assume everybody understood. If not, then maybe if you look back my theory part again, you will understand. All right. What we'll do, we'll just take a few more for numerical example today. Okay, and try to solve. Now we'll take up few examples. Uh, this kind of examples are actually solved in your book itself. Okay. Suppose uh, suppose I have a straight current carrying wire, a straight current carrying wire, current carrying wire, which is carrying current 12 ampere. 12 ampere current it is actually carrying. Okay. Now it is, suppose this straight wire is bent. The wire is bent into a semicircular form. Into a semicircular form. Semicircular form of radius. Okay, radius 2 centimeter. 2 centimeter. And the figure, it is actually shown in the figure. See the figure. For one, it is, I can bend it two ways. One is like this. Okay. I assume this is a semicircular path. One is this one, and another one is exactly opposite. Both have suppose same dimension. Okay, semicircular arc. Okay, so in case of this, the current direction is this way. Okay, so what you have to do, you have to tell me the magnitude of the magnetic field and the direction of the magnetic field and the center of the arc, both cases. So this is suppose A, this is for B. So at the center, you have to find out the magnetic field at the center here, or this also here. This may not be very much semicircular, just to show you a representative figure. Okay, so the radius, this is 2 centimeter, and the current it carries actually 12 ampere. You have to find the magnetic field at this point. Okay, at the center. Okay, so who is going to solve this? Priyadarshini, you have to tell me now. Ayesha, you have to also see how you can do it. So which formula, first of all, which formula are you going to use here? That you have to see first. Okay, see, I have this straight portion as well as my curve portion. You can see this is 1, this is 2, and this is 3. You have 3 portion of the wire. Among them, 2 are actually straight and another one is a semicircular arc and having certain radius. So look, uh, I'll use Biot-Savarts law. Okay, B is equal to mu 0 I by 4 pi. Okay, this and then ideal sine theta. Okay, sine theta. This is obviously dB. You have to take integration for the whole. So sine theta divided by r square. So this is what you have to use here to solve this problem. So you might be thinking, then how to do with this straight line? Straight line. For the straight line, look here. What happens? So this theta is actually with the current element and the radius vector, where you are calculating magnetic field. So if I just take this as radius vector small r, look for this straight path for straight wire. So this is the r, right? So what is the angle between DL and R? If this is DL and this is R, the angle between them is 0 degree for both of them. So sine 0 is 0 for the straight. So B for 1 and B for 2 will be 0. In this case also, if this is 1, this is, sorry, not 2, this is 3. This is 2 and this is 3. Both cases this same thing. Okay. In both cases the same thing. And now you have to see what is the magnetic field for this semicircular arc. So semicircle means what? So this see see if I take a small element here. So as I said, this you have to take the direction of that element in the direction of current, and you have to draw the tangent over there. So tangent and the radius of the circle always makes an angle 90 degree. Okay, makes an angle 90 degree. So here theta will be 90 degree for the curved path. So DL, now look, if I just do the integration for this part, or take the summation, whatever you like to do. So look, if this will be mu 0 I by 4 pi r square, and this will be pi r simply integration of dl, because this is the perimeter of the semicircle, and sine theta anyway sine 90 degrees is 1. So what you get? Pi goes up and 1 r, like that it goes. So mu 0 I by 4r. Okay, this will be the answer for this one. So similarly you have to find out the for the other case also. Anyway, for both cases the magnetic field will be the same magnitude wise, but the direction may be different. Okay, direction will be different. So for the one, for this one, for A and for B, the direction will be just opposite, otherwise things will be all similar. Okay, so this is how you have to apply Biot-Savarts law for this kind of wires. Okay, now I'll take a current carrying wire which is 5 ampere, okay, 5.0 ampere. Okay, so this thin wire, a wire which is carrying current, this actually bent has been bent to get a special figure like this. Figure is sorry, the figure is something like this. One part straight and rest of the part is kind of semicircular, okay, like this. The current is flowing in this way, suppose this I, and one more information is given. Suppose this is the center of the circle, so the angle this wire is subtending at this center, this is O, this is actually given as 2 pi, which is 90 degree, okay, which is 90 degree. And suppose this is R, okay, this is capital R, and that R is given R means the radius of the circular part, 120 millimeter, okay. And then you have to find out the magnetic field at this point O. B at O. You have to find out B at O. So how do you do that? Kirtana, can you try this? And all others? Priyadarshini, then Samhita, Sahitya Rao. Okay, so you people can try, all of you can try this problem. See, you have to simply apply Biot-Savarts law. So you have got actually two parts. One is curved part, another one is actually straight part. Straight part, and this is finite wire, right? This is a finite wire. So what formula are you going to use here? For a finite wire, same thing, mu 0 I by 4 pi. Okay. I'm writing the general formula you have to use for this problem. This is then sine phi 1 plus sine phi 2. This formula for the straight part, and the curved part, you know, I had already written for you. Curved part, again, this Biot-Savarts law. Okay. So suppose this is mu 0 I by 4 pi, then I summation over dl sine theta by r square. Okay, this is what, these are two formulas you have to use here. Okay, I'll just wait for 2-3 minutes. If you people are saying that you are not able to do or something, then I'll just solve it for you people. But these are the kind of problems you will face when you go for a competitive exam, or sometime maybe if the board paper is little tricky, then this kind of problem may come, okay, in your exam. So next day we'll again learn the rest of the part, their ampere circuital law, and then solenoid, toroid, etc. We'll learn over there. Okay, so Kirtana, are you trying, or shall I discuss the problem itself? Others
I'm
are not
trying.
responding. At least you are responding. Are you trying, Kirtana? Okay, so shall I wait for 2 minutes?
Yes, sir. Yes. Yes, sir.
Okay, okay then.
Sir, please you carry on, sir. It may take some time.
Okay, so okay, I'll just discuss this problem so that you can. I may not do all the calculation part by part. I'll just tell you. Suppose for the straight one, suppose I say this is B1. Look what I have to do. I have to draw this one. Okay, perpendicular bisector. So suppose this is phi, so this is also phi anyway, perpendicular bisector. So what you get is actually in this case, if I so this is phi, right? So look, this is the formula I'll just apply for this particular problem. So mu 0 I by 4 pi. What is A? A will be this length. Okay, this is the length will be A. So this is R given. Okay, so if you just take the projection of this R along this direction, so what you get, that is actually R cos phi. R cos phi. Okay, and here you'll get both are phi and phi. So you get 2 sin phi, right? So now look here, mu 0 I, and this is suppose this is sin phi by cos phi, so it will be 2 pi r into tan phi. Okay, tan phi. So this is B1, and look this one, the direction for the state where actually magnetic field is going into the field. Okay, going into the field, and for the curve also will go into the phase. Okay, that also will be actually going into the phase, so both will be additive. Look here, in this case the curve path, see, you have to find out the arc length, otherwise things are all right, all things are okay. Okay, so all things are fine, only thing is you have to find out, see, for the curve path this is the r, so r is r, you know, so mu 0 I by 4 pi, and then this is r square, and sine, you know, like, see, this is a 90 degrees, so sine 90 degrees is equal to 1, and see, summation of a dl you have to write, that means the length of this hole. So you know, like, this is 2 pi, right? Okay, so what is this angle, rest of the angle? 2 pi minus 2 pi, isn't it? Rest of the angle. Okay, you have got like this, so this is 2 pi, 2 pi, so rest angle will be actually 2 pi minus 2 pi, and you know, you will be writing, so this is the arc length I have to get, hold the arc length. So you know, like, arc length by radius is angle, right? So I'll be using this concept over here. So if I do that, then see, so my arc length will be is equal to r in theta. R is the r, you know, theta is actually the angle, the whole angle, this one, so it is 2 pi minus 2 pi. Okay, now just go, so r goes off, so look, if you just take 2 common from here, so you get mu 0 I by 2 pi r. Okay, this factor is common, and here you will get pi minus 5. And you know, look, what is 5? 5 is 45 degree. So if you just add these two, b1 and b2, then you get the whole answer for. Okay, so I is given, r is given, you have to just put the values and see, r is actually 120 120 millimeter, and this one I is 5 ampere. So if you do all the calculations, adding, see, total B will be B1 plus B2, B1 plus B2, and phi will be actually, phi is pi by 4. Okay, so if you put the phi after adding this 2, then you will get the answer. So what is the final answer? I just write the value for that, and you people have to verify and tell me next class whether you got this answer or not. So I have given the hint, not hint, in fact I have just done more than half. You have to do rest of the part. Okay, you can do the rest of the part. Okay, so this will be actually magnetic field at the center. Okay, at the center at O. Okay, so I think I'll stop it here with this. You people have to be very much prompt, and you have to remember these formulas and all, and how to apply these formulas. You have to be expert in that. Okay, if you become expert, then you'll be able to crack any competitive exam. And you just remember that from this chapter onwards, there are 3-4 chapters from where JEE Main, JEE Advanced, and even in the NEET exam, there will be many questions from this magnetic effect of current, then magnetic material, then induction, electromagnetic theory, and AC part. So many questions will be there from here wherever you go for any competitive exam. So I think I'll stop it here today. I'm sorry for those who had joined today, like newly. They may not have I don't know whether they knew this Biot-Savarts law and all, but if people can go for the previous lectures and see, I have already given lecture on this Biot-Savarts law, how to derive the formulas, and for the straight wire, anyway, we have derived today. Okay, so we'll meet again on the Sunday. So on Sunday we'll take up Ampere circuital law, and the application of Ampere circuital law. We'll apply those that law in toroid and solenoid, and we'll try to pick up few numerical example then and there. Okay, then see you on Sunday. So